Good morning, everybody. How many? Number 7. Okay. Hello, the Noro Asila.
Hello. Good morning.
Good morning. Nice to meet you. We are first to meet.
Nice
Okay.
to meet you too. How are you? How everyone?
I'm fine. Yes, the Asipukan is talked about yes, a lot of things to me, and you are very important. The position to the performance to perform the project. So really welcome APRP working group.
Yeah, thank you. Actually, in UPM right now, in University Putra, we are really looking forward. Actually, we have some survey on the usage of HPC in UPM.
Yeah.
And this is like a very right time when we got this project. So because we really need this HPC. So I think this is like just dream come true for UPM. So I really thankful by joining this project.
Yes, I think it's our the project is very good effect to your country and in my country for Asian beneficiaries. So let's say it's collaboration with in the future.
Yeah,
And
I'm really really agree and looking forward for this. Thank you so much. Yeah.
Yes, me too. Okay, it's time so it's 12 to 9 o'clock. Good morning, everyone. I'd like to start this APRP working group APAN the 53rd meeting. So the first, I will introduce APRP working group. And can you see my presentation? Right?
Yes, I can see.
Okay, let me start. And the first time is I want to introduce the APRP working group, and also is introduced in the session 1 and the session 2. So the APRP working group is meaning is Asia Pacific Research Platform. It since 2018 initiated in the APAN the 45th 2018 Singapore meeting. And our objective is to promote the HPC ecosystem in the Asia Pacific regions. And we want to engage APAN members and ASEAN countries to establish the big data superhighway and the combined distributed computing resources. And then finally, we want toward the setting up on the Asia Pacific Research Platform and become a part of the global research platform. The global research platform is from PRP project in the United States is by NSF. The PRP project is based on science DMG technologies. It means the link the science DMGs and the learning the distributed computing on their environment. So today, the next slide is I will introduce about is a new project from TNCC, the Asia Connect Fifth Core project. At the time is I will explain about more detail. And the APRP working group target is academia and the university industry in Asia regions. We have the executive and the members. Chair is me, and the co-chair is Andrew Howard from NCI Australia. And the secretary is Asipu Khan and from Perdana University in Malaysia. And today we have 2 sessions. Session 1 is from 9 o'clock to 10:30, and the session chair is me. The first slide is I just briefly introduce APRP working group and the session information. And the second slide is the presenter is me and the introduction of Asia Connect project. The name is building a high bandwidth distributed HPC. The third presenter is IFSPA from NSCC Singapore. And the title is Research at the Speed of Thought, a Golden Age for the Global RNA Community. And the fourth presenter is Ki-Hyun Kim from KIST in Korea. And his title is the career update and the research platform. And the sixth, the presenter is Vikas Sinha from India. He wanna talking the Kolkata Tier 2, the past, the present, and the future. Its relation with is grid computing and big data storage. He will explain about this the sun in Switzerland and some the physical the particle physical areas. This topic is the very close relation I think with in APRP environment or the infrastructure. The last slide is presenters is Bernard C from NSCC Singapore, and his title is Singapore Update for the APRP. The session 2 is from today and from 11 a.m. to 12:30. And the session 2 is first the presenter is from Andrew Howard and his the expert staff from NCI. The title is Introduction of NCI Cloud System. I think this slide is as the session keynote speech, the session 2. And the second thing is Presenter Asif Khan from Perdana University in Malaysia. His title is ASEAN Update and the Introduction of Bioscience. The third thing is presenter is Kyu Kim from KIST in Korea. His title is Science IoT Over Science DMZ. And the fourth thing is from 12 to 12:15. Its presenter is Asif Khan from Socorro IVA University from in Pakistan. His title is Pakistan Update and the Introduction of AI Science. So finally is closing and on me. Yeah, this is our briefly our session 1 and the session 2 introduction and the APRP introduction. And then I will talking about is the first presentation, the introduction of Asia Pacific, Asia Connect project. Okay. Hello everyone, and I'm Jong-hoon Moon. I'm working for KIST in Korea, and therefore especially working for KoreaNet, which is the Korea, the research and the education open network. And also I'm in charge of APRP working group in APAN, which is Asia Pacific Research Platform Working Group since 2018, as I mentioned. Today, I will talking about there's a building a high bandwidth distributed HPC project as the Asia Connect project, the fifth core by Tae-in. And this slide is the overview of this project. It belongs to work package 4. And the participant countries are 4, which is the Korea and Australia, the Malaysia and Pakistan. And the request budget is around this 150K euro. And the lead applicant is me. And we have 4 the co-applicant. Those are the Andrew Howard from Australia, Asif Khan from Malaysia, and Noor Asila Watia Abdul Hamid from Malaysia, and Seed Asif Raja from Pakistan. This slide is important. This slide is a background of this project. And the data explosion is a science and technology drives the demand for high capacity networks for accessing and the computers, storage and the collaborations simultaneously. It brings many restrictions on the generation, transmission, and the utilization of research data. In recent year, the ESNet and the UCSD collaborated in the US have developed and utilized science-based big data superhighway to send and share scientific big data with the leading research institute or the university. In the case of the US, it was carried out as the national project supervised by the NSF, Connecting Science and Technology Research Institute in the western part of the US to Science DMZ and enabling the high-speed transmission of big data, we can call it a PRP project. In addition, this big data network is the central infrastructure system is expanding and developing into the global environment we can call GRP, Global Research Platform. For example, the figure 1, the left side, shows the distributed computing resources integrated through PRP infrastructure and the scientific result about the analysis of CO2 using the distributed computing method. It is possible to link computing resources distributed to research institute through the big data network infrastructure without possessing high-performance computing. It means that a specific researcher delivers a research result without possessing high-performance computing. And the figure 2, the right figure, and shows the urban flooding research using distributed computing resources and the science data for LSTM analysis method for climate analysis. The infrastructure links distributed platforms at many Korea research institutes through the National Research Network. It is the KREONET. The participating institute share the HPC resources for their researches. The purpose of this project is a method to enable public high-performance computing resources to be delivered to underdeveloped and developing countries in Asia through TAIN network. We propose a platform that transmits not only the data over the network, but also computing resources. In this proposal, we aim to establish a science DMG-based research platform, a high bandwidth distributed edge environment, and it will be shared in Korea, Australia, Malaysia, and Pakistan. That is, we will build a high-performance computing servers that provide the computing resources by CPU, GPU through a specially designed high bandwidth network over TAIN. And it will be learned for bioinformatics and AI-based science in Malaysia and Pakistan. So this is a basic concept of this project. The where science DMG-based high bandwidth networking architecture is designed in participating countries via TAIN. We will interconnect available computing resources in a distributed manner. The resource of computing servers will be managed by container cloud technology and also the blockchain authentication. And the role of each participants are the South Korea and Australia providing infrastructure expertise and infrastructure capabilities. And Pakistan and Malaysia providing the application expertise. To implement these, it is divided into 3 activities, and each will achieve the detailed goals. Activity 1, building a big data superhighway based on TAIN among the participant countries. Activity 2, the building a distributed HPC platform. And activity 3, the presenting pilot use cases. Activity 1 will implement the science DMG technology to improve the utilization performance of the physical network based on TAIN, while activity 2 will implement the container cloud technology and the blockchain authentication technology for a user authentication system to the distributed HPC, relying on a high performance physical network. Activity 1 and 2 are applied to all participating institutes to establish big data and high performance computing transmissions and sharing the environment among participating institutions. AI and bioinformatics-based science research applications and use cases can be implemented in the 2 Asian beneficiaries. Activity 3, these applications are meant to improve the educational and research functions of the institutions. To build a big data superhighway based on TAIN, there are 3 steps to enable these environments. Interconnecting, the first one is interconnecting participant endlines via TAIN. To build a big data superhighway system, KREONET, ARNET, and MyREN and the PRN of participating countries are linked with the science DMG technology through TAIN. And the second thing is installing DTN in each participant institutions. Each institution that constructs a science DMG environment by building a DTN, data transfer node, which is perform transfer accelerator function. DTN is used not only as an accelerator for data transmission, but also as a container-based distributed computing resources. So it is used for various computing tasks based on CPU, GPU, memory, depending on the need of application researchers. Third one is measuring the science DMG using a monitoring system. The big data superhighway system is constructed through mutual trust zones of each institutions. Therefore, in order to guarantee the performance of such a network system and the computing resources, they are monitored in real time through the Persona and the Prometheus-based Grafana. And to build activity, this slide is an activity tool. Is to building a distributed HPC platform. There are 3 steps to enable this platform. The first one is building a platform to manage CPU, GPU, computing resources, including storage. So building a container-based cloud system that will provide not only a single container, but also the programmable environment to orchestrate with remotely distribute the computing resources. This platform is to provide high-performance computing power with the distributed computing resources. The developed system will be able to collect the CPU, GPU resource for large computing power to computing a big job. Therefore, a single large active job in use will be able to use the whole computing resources like HPC. So we are using a Kubernetes to build a platform. The Kubernetes is open source, is used to manage CPU, GPU resources with the containers and also manage the self-storage. Second thing is a blockchain-based ID federation. To manage user account, we want to using the blockchain-based self-sovereign identity technology that allows users to control the use of the personal information. Third thing is building an easy user interface. It provides an easy user interface by building a portal that runs on the platform over a high-performance network. And AI and the bioinformatics science researchers and the university students will use this system. This slide is about this activity 3, which is presenting the pilot application use cases. We intend to establish a platform where distributed resources can be used as HPC resources and demonstrated the use of AI and bioscience targeting ASEAN beneficiary in a high-performance network environment, as shown figures. It will be supported high-throughput science research and contribute to human capital development to produce scientists who are able to perform well in the research area of the new science. This table is a deliverable. The science DMG built on the physical network according to each activity will generate output in the form of DTN network hardware. And the distributed HPC function will generate output in the form of the container cloud software, which will link distributed resources based on science DMG. In addition, the AI science and the bioscience use cases for ASEAN beneficiary countries will demonstrate the applications through training and publication and or the formal report. KISTI and the NCI in charge of D.1.1 to D.2.2, and the others, 2 things, use case for AI science, and the other is bioscience, is by Malaysia and Pakistan. This is the official milestone and the timeline. The activities all produce a meaningful result which will make up the deliverables, and will indicate milestones as a table. And we have 8 milestones to achieve the goal to build the distributed HPC platform. The major result of the project will be the high bandwidth distributed HPC infrastructure distributed at the 4 participating countries and the application cases using these. An important outcome will be the achievement of the technology on a distributed platform that links the GPU and the CPU resources distributed in Asian countries with a high performance network infrastructure over time. The first one, the networking and the computing infrastructure of 4 NLANs based on TAIN. The second one is promoting ASEAN research, the education by utilizing TAIN-based distributed HPC resources. The others is several outcomes which will be derived. It will benefit Pakistan and Malaysia, where HPC resources are relatively scarce. And the next is the sustainability of the activities. The first one is using the APAN, the APRP working group for managing and operating. The performance and the effectiveness of the high bandwidth distributed HPC, the achievement of this project will be continuously managed and upgraded through APAN, the APRP working group. The expanding the use cases in Asia. The result and the outcomes of this project will serve as a proof of concept for the beneficiary countries. In addition, the result and the outcome also serve for international research community, such as APBioNet. The APBioNet is the international research community that is dedicated to the advancement of the bioinformatics areas. The third one is motivating the further collaborations via TAIN. The countries in low bandwidth network environment in Asia can also share sufficient high performance computing via TAIN. It would motivate future national and international network improvement and collaborations. So far, I trying to introduce in the building a high bandwidth distributed HPC project. Thank you for your attention and listening. Does anybody the question or the comment? Okay. Okay. I want to introduce the next speaker. It's Pop from NSCC Singapore. He will talking about the vision of our topics. Yeah, please go ahead, Yves.
Thank you very much, Jong-hoon. Give me just the time to put my presentation online. So I think that should be okay. First of all, thank you very much, Jong-hoon and Andrew, for inviting me to share some thoughts on APRP. And again, as my title says, the RP research platform with the X standing for P for AP, which is us, the N and G. We'll go briefly through it. And again, the goal of the whole exercise is to help research. And if we look, first of all, at the network itself, it's good to remember that the Global Research and Education Network has evolved quite a lot. In fact, over the last 10 years ago, was in fact the first 100 gig connection which was demonstrated between Reykjavik in Iceland and Holland. That was for the Tirina meeting in 2012. And there the idea came to have 100 gig across the Atlantic. That happened in 2013. That was also at the Tirina meeting in Maastricht. Then on the Pacific side, we had the Bandung challenge at the APAN48, I think it was, and that resulted in the first 100 gig for the supercomputing 2014, in which a number of us participated, and the rest of is history. If we look at it today, this map here shows the 100 gig connectivity in the research and education sector. And one big difference, of course, is that nowadays we are talking about 15-year IRUs, indivisible right to use, so long-term leases. So we act like carriers, and of course, that helps all the research and education projects we want to accomplish. Why do we need research platforms? I think one of the main reasons is for the major projects. And again, if we look at the CERN, high energy physics in Geneva, if we look at the astronomy projects like SKA, LIGO, which looks for gravitational waves, if we look for ITER on the fusion side, these are huge instruments, and these huge instruments are of course shared by hundreds of scientists distributed over the world. Now, another element which is quite important and gaining in importance is the fact that the supercomputers are also to be considered as instruments, because everyone now in the major countries at least is going for exascale. We know China, the US, Japan, and Europe, they all put $1 billion plus budgets to be the first ones to really harness exascale. And right now, RIKEN in Japan is #1. The US has 2 #1s very soon. China, APRP has also 2 exascales machines, which they did not submit in the list at this point in time. So it is growing. So again, the goal of research platforms is essentially to allow within disciplines like astronomy, like energy physics, like genomics, more and more genomics is important, the weather forecasting, again, with the climate changes, everything which is weather related gets a lot of funding. And of course, collaboration also has been quite important for everything which was related to COVID over the last 2 years. So this is basically the reason again for these research platforms. It's distributed, it's data focused. Again, we need to gather data from instruments, we need to compute the data, and we need to store the data, and storage is more and more important. So these are the 3 vectors which we have, and everything has to be done in a secure way. Security, we all know, is more and more important, and researchers have to be comfortable and be able to do the research without having to configure networks, etc., etc. APRP, Jong-hoon was mentioning it. It was first proposed in 2017, and we set up the working group within APAN. And thank you, Jong-hoon and Andrew, for your excellent work over these last 3 years. It's great to see the progress we are making, and it is only a beginning. This year, we had the Data Mover Challenge. I think Bernard C. will talk more about it later this morning or this evening. Depends where we are. And again, it was a great success. And thanks to Andrew for being a chief judge of a quite interesting project here. And again, the DMC is part and parcel of the famous research platform effort, because within a research platform, data movement is, of course, of utmost importance. Asia Connect as a key enabler of APRP. Jong-hoon just gave a presentation on the new project he has now started together with Australia, with Malaysia, and with Pakistan. Again, congratulations. This is a great, great project. So we have supercomputing on one side, and we also have the application side with the AI and the bioinformatics. We saw this slide in Jong-hoon's presentation. So this is the new Asia Connect project. Now, if I think of the old one, or the one from last year, was in fact the first Asia Connect funded project, which was headed by Lawrence Wong from Singapore, who was a PI for that project. And the title of that project was Large Data Transfer Infrastructure and Training. So that project involved Indonesia, Thailand, and the Philippines together with Singapore. That project finished at the end of last year, was quite successful. Now, the result of that project is that these countries also have DTNs, data transfer nodes. So one thing I would suggest and propose going forward is later on, maybe later this year or next year, to hook up these two projects so that we have 8 countries in the Asia Pac creating a real APRP, which is quite extensive and which has staying power. And again, thank you, Asia Connect, for making this possible. I was asked also to give some retrospective on the, excuse me, the GRP, the Global Research Platform. Global Research Platform had its first meeting in 2019 in California, was supposed to meet in 2020 and 2021, and obviously with the COVID phenomenon, the GRP last year was virtual. And last week at the Supercomputing Asia session, we had a mini GRP, which was chaired by Joe Mambretti and Francis Lee, and had 14 presentations, which were extremely interesting. And in fact, the highlights of the GRP session, if you allow me again, of the 14 presentations, we had 4 related to projects. One was a presentation on the astronomy side of the SKA, the Square Kilometer Array. It was given by Richard Jones. And the second presentation was on the Vera Rubin telescope in South America. And again, if you look at these 2 projects by themselves, they will generate astronomical amounts of data. It's astronomy, but they're talking about zettabytes of data collected. On the genomic side, Singapore gave a presentation of the Singapore 100,000 Genome Project. And we also had the high energy physics. And again, if we add all these volumes, quite impressive. Joe Mambretti and Jim Chen gave an overview of the major projects. I would encourage each of us to look at them, because some of them I think are of interest to our Asia Pac research and education community. One which really caught my attention is the Fabric/Fab, which is the international component of a Fabric. Again, this is a PRP or a research platform, but with more advanced instruments at the end. Again, a lot of effort on a GPU and also on FPGA. So it again pushes the envelope forward. And one very interesting presentation was by Dong-Kyun Kim of KISTI, who gave quite an interesting perspective on the new CRIONet plans, for CRIONet S, as they call it, and that includes private 5G, very important these days, network intelligence, again, very important element, and also a notion which was new to me, which is VDN, for virtual dedicated network, again, closed user group in a research platform environment. Another session we had at the Supercomputing 22 last week was APRP and DMC. On the APRP side, we had Joe Membretti giving an overview of what had happened at the Supercomputing 22 with the NRE, the network research experiments. Again, I think there were 13 or 14 experiments approved, quite a number of them extremely interesting. And again, some of them we have joined in the past and we should join in the future. And the next supercomputing will be in November in Texas. And I hope a number of us will be able to go. A very interesting presentation also on the physical layer was by Rod Wilson from Siena, and whose talk, the theme of his talk was the OFC net, the optical fiber conference net. In fact, the OFC is happening in California as we talk. It is this week. So the idea of OFC net, as OFC happens every year at the same place, they are setting up a fiber of their own between the venue and the scenic network on which the PRP, the research platform of California, also runs. And ultimately, that setup will allow for 34 terabit per second transmission. So quite interesting. So we will be able to push the envelope on the data mover challenge, another order of magnitude. Other very interesting presentation was by Kees de Laat and Paola Grosso from University of Amsterdam. And their Kees and Paola put the emphasis on everything which is related to security and confidentiality. And their university did quite a lot of work in that respect. And they put that now in the context of the creation of what they call the AMDEX, Amsterdam Data Exchange. And it was quite impressive. 20 years ago, I participated in the creation of what became Netherlight and the Amsterdam Exchange. And these are two of the major exchanges in the world now. And I would not be surprised that the AMDEX will go in the same vein. On the application side, we also had KAUST giving quite an interesting presentation on the use of a genomics database in a cloud environment with all the aspects of confidentiality, etc., etc. And of course, we had Jong-hoon, who talked about the implementation of the Korean research platform. And again, congratulations, that research platform can really be a model for all of us. And of course, the winners of the DMC challenge were announced, and the winning team was Siena with the iCare and the university in Utah. Now, the model we're following, as Jong-hoon was mentioning, is the US model, which went from PRP, Pacific Research Platform, to National Research Platform with an intermediate step in the middle. If we look at it very briefly, we had the CNIC, again, was funded, all of these projects are funded by the NSF. That started in 2015, based in fact on a concept developed by the Department of Energy in 2010 with the notion of a science DMZ. CNIC was a tremendous success. Funding ended in 2020, but now has been refunded on a year-per-year basis. A second funding has been to expand the PRP to have a more US-wide coverage, and that was also under an NSF project with Larry Smarr as PI, and we had our friends Tom DeFanti as who spoke at one of our conferences as one of the co-PIs. And again, that grew to the other coast, and again, it went on for a number of years and allowed the evolution of the whole research platform concept. Expanse and NRP, explained by Larry Smarr, again, expanse is the distributed access to supercomputers, to instruments, to storage as implemented in California. Again, a nice model. Then the new project with Frank Wertwein as a PI, because Larry Smarr retired in the meantime. And that also is quite a nice project, which we should have a look at, because we can learn some things from them and maybe also emulate some of this on our side. Again, this describes the project. So you basically have the expands, the exceed, and then also on the right side, you see the famous composable side. So this is also something we should follow. This year to 2026, we have the next phase, which really will bring NRP, National Research Platform. Again, it will not be totally national, but again, money has been set aside by the NSF to fund HPC resources, to help in setting up a distributed data infrastructure. And again, the goal is to help data-intensive science. And of course, they are all quite eager for international collaboration. If we look at the PRP, as I said, was finished, and there was a kind of a capstone seminar early this year where they really took the stock of the options of the achievements. And I think innovation, again, it's quite important. And I think on our side also, we should look at the FPGA going forward. We did not do that so far. The GPU, TPU, DPU, everything which is now quite fashionable. And again, open source software and projects are quite important. Scaling and the sustainability, not to mention the security. Security is very important. That was again illustrated by Jennifer Schopp's talk yesterday, and it's quite important because again in a research and education environment we are becoming more and more like carriers. We have interconnected networks, so we have mutual backup, we have a mutual transit, a mutual overflow, and so we have to manage that quite efficiently. Suggested next steps as last slide, expand our footprint, combining the topologies of the two Asia Connect funded project, as I mentioned. I think we should plan joint demos at SC in November. We should give presentations to the relevant conferences, ISC, for example, in Germany, ENC in Trieste, next to GRP, which will be in Utah this year, and that will be likely face-to-face. Nordinet, which will be in Reykjavik in September, and of course SC22. Standardized and document APRP implementations, including recommended DTN configurations. I think that's quite important because DTNs have been growing. There are small ones, there are medium ones, there are big ones. The DTNs with GPUs, the DTNs now with FPRGs coming very soon, etc., etc. So I think it would be good on an Asia-Pacific side that we have a recommended or a couple of recommended DTN configurations at least for our local implementations. Increase our outreach and interaction with the HPC community and select application domains. Again, very important to talk to application domains because without applications, there's no need for a research platform. And we have to do more, some of us, and follow Korea's example in implementing domestic research and research platforms. And again, as I said before, evaluate the US experience. As we see, we have the OSG, the open grid, we have the expense approach from PRPU CSD. As I mentioned, there is Noted. Noted is a development by the CERN in Geneva. Fab, which is the international part of Fabric. Now there's P4 programming and P4 switches, another team which we see more and more and more. And it would be good that we get some expertise in P4 also. And I would suggest that we prepare a go-forward plan and present it as a keynote at an upcoming APAN meeting. And of course, we have to plan for the next iteration of the DMC challenge. This will conclude my talk. Again, thank you for your attention. And as I like the Eric Fromm statement, creativity requires the courage to let go of certainties. Thank you so much.
Yeah, thank you, Yves. Anybody question or the comments? Okay, thank you again, Yves. I see you. And next presenter is Ki-hyun Kim from KIST in Korea. The title is the Korea Update and the Korea Research Platform. Yes, Ki-hyun Kim, are you there?
Yeah.
Okay, please go ahead, your presentation.
I don't screen share.
The Yves, did you off the screen share? Okay.
Okay.
Go ahead, Ki-hyun Kim.
Yeah.
Okay, I can hear you well.
Yeah. Hello everyone. My name is Ki-hyun Kim. I work at KIST. I'm in charge of a development platform in KRP and the Asia Connect project. Today, I will explain platform development in KRP and the Asia Connect project. The global research trend has changed since 10 years ago. Big data is overflowing with the advent of super facilities that produce large amounts of data from research equipment. It will change from the existing simulation-oriented research environment to a research environment for processing and calculating data. Although these types of research have changed, the technology of the network has not been able to support these research changes. Accordingly, the global trend has changed to big data superhighway using science DMG. So we building a Korea research platform. So I will explain about the Korea research platform. Our platform is based on PRP Nautilus system. KRP is an infrastructure for research and educational institutions to carry out scientific research in various fields. Through the KRP, convergence of nation science and technology can be achieved. KRP consists of two components. Components are data network system and AI platform integration system. Data network system is science DMG, so safe on security aspect and transmit big data without packet loss using DTN technology. AI platform integration system is a combination function that process GPU computing and AI programming. The science DMG construction schema configured in this way is as follows. Currently, we have built a DTN server to configure science DMG between KIST and the affiliated research institute. Each institution's border router configure one network line separately to measure the DTN server and network transmission speed. Install and configure the personal server. Currently, there are 8 institutions established as follows. It is an infrastructure built using science DMG. Currently, a total of 8 institutions have DTN installed, and after configuring the DTN installed in 8 institutions by connecting them with Kubernetes, a container-based computing environment is provided. Looking at the overall computing resources, the GPU consists of 19, and the CPU is about 400 cores. You have seen the statues of infrastructure construction so far. Next, I will tell you about the process of developing an AI research environment providing platform. This platform is all configured using open sources, and a web UI is developed and provided to users to use the open sources installed based on Kubernetes in an integrated way. This system is configured so that only authorized users can utilize computing. So even if it enters, it can be used only with the permission of the administrator. Rather than explaining all open sources, I will briefly explain the important open source for each function, and then tell you about each module, how to use the system. The structure of the AI research environment providing platform is as follows. The most important role among each component is by far the Kubernetes cluster module, and through this module, all functions are developed to operate on the container basis. From the user's point of view in this structure, it consists of login, computing, transfer, storage, and monitoring. The transfer part is transmitted using DTN, and the login is configured to log in through the ID federation system developed by KISTI. The federation system name is CAFE. And I will explain in more detail about the computing and the storage monitoring part. First, let's talk about the computing module. The computing module is divided into two parts. Describe computing environment and distributed computing environment. The individual computing environment is configured so that individual users are allocated the computing resources. They want to create a container, and then the create container image is created based on Jupyter Notebook. Jupyter Notebook is an open source web application that allows you to create and share documents, including live code, visualization, and so on. And is mainly used for data pre-processing, statistical modeling, and machine learning. Specifically, it is a web-based tool that allows you to interactively manipulate and visualize data in real time. When users create a container, a web URL is automatically created, and if they enter through the URL, they enter the Jupyter Notebook UI as shown in the figure below. The AI code interface that can be used inside provides various interfaces such as Python, TensorFlow, PyTorch, Keras, and MPI. Kubeflow is free and open source machine learning platform designed to enable using machine learning pipelines to orchestrate completed workflows running on Kubernetes. Kubeflow provides various frameworks for constructing researchers' machine learning models. The purpose of Kubeflow in this model is for distributed computing. The operator function in Kubeflow provides distributed computing environment. Distributed computing environment provides massive computing using all GPUs in worker node. To use Kubeflow's distributed computing, you need a parameter server and a worker server. The Kubeflow module is the core module in this platform. Next, in order to perform the computing module, we need a system for storing images. Harbor is a tool for private image registry. In our system, it is used to provide images in private and public environment. In the case of private image, users store the images they create in Harbor, and then the provided system provides an environment where users can share them according to the user's permission. The storage module consists of SEP and loop. SEP Storage is an open source software-defined storage platform that makes it easy to manage storage servers with software. It provides object storage, block storage, and file system interfaces. and look to be used together, act as an orchestrator to link Kubernetes and SAP storage. The size of the current provided storage server is about 300 terabytes. And when configuring the storage, it is configured as object storage. Object storage enables enable data transfer with other users, and when object storage is configured, it is currently configured to link with other cloud platform to transfer the data I use to the cloud platform. Next is the monitoring module. The monitoring module used Prometheus and Grafana. By using the Kubernetes resource monitoring API, the resource information of our DTN servers is sent to Prometheus to collect index values. Using the collected values, Grafana components the web UI and displays it in graph form. This is the graph configured in the currently configured monitoring system. Yeah, next, I will tell you about the plans that will be carried out in the API project. This picture is for the establishment of Science DMG in Asia Connect project. This project establishes Science DMG in Korea, Australia, Pakistan, and Malaysia, and connect distributed DTNs in Asia to establish Science DMG. After that, the API platform is developed using the DTN built in each country as a project to help AI research in Pakistan and Malaysia. This platform will expand, and we will continue to work hard so that many researchers can use it for AI research. The structure of the APRP platform will consist of an environment similar to that of KRP. The configured platform will allow Pakistan and Malaysia researchers to connect and conduct AI research, thereby expanding the field of AI research and gradually increasing the number of cases. In addition, we plan to expand the scope of resource by conducting a federation using Admiralty for both APRP and KRP platform. Accordingly, we will provide an AI research environment for the Asia region. In addition, we plan to support research collaboration and increase research productivity in the Asia region. Thank you for listening to my presentation.
Okay, thank you, Ki-Young Kim.
Yeah.
Anybody comment over the question? Yes, okay. The next speaker is Vikas, is Singhal, but he is not in here. Hello, Vikas. Are you there? He got some problem to enter this the Cuba environment. And the next presenter is Bernard C. And also he's not in here. And he
I just reached out to see if he can join.
Okay. Yes, he will be joined shortly. Please wait a minute. Yes, and please wait for him. Okay, now the Angel call him now. The Vika Singhal is appears in our the list. Hello, Vikas.
Hello.
Hello,
Yeah.
hello, Vikas.
Yeah. Hello.
Can you give a presentation now?
Yeah. Just can you give me 2 minutes? Means I have to download on my mobile. Some problem in other device.
Okay.
I have sent you. Can you share? I have sent you on my mail, on your mail.
Okay, nice to meet you.
Nah, yeah. Sorry.
Yes.
Apology. It's
Yes, go ahead whenever you're ready.
yeah. I am ready. So can you share my presentation if possible?
I don't have your the PPT or the material.
I have sent you just now my
Okay.
sorry.
Okay, I will check.
One.
Okay. Okay, I got it. And I will I screen share and you can call the next. Okay.
Yeah, sure.
Okay.
I will tell you.
Wait a minute. Okay, go ahead.
Yeah. So good morning, everyone. So myself, okay, on the first slide, yeah. So I am just going to present about this Kolkata Tier 2, and as topic is past, present, and future. So I will update about all the things which we are. So first, as per this slide, it's an India map, and we are situated in the Kolkata. In Kolkata, Bidhan Nagar is a place, and then down picture shows that our institute. So as you know that Kolkata is the capital of our West Bengal state of India, and it is known as City of Joy, where many great persons born. Mother Teresa, means they were here. Rabindranath Tagore, Satyajit Ray, J.C. Bose, and S.N. Bose. So it's reached as far as academic culture is concerned. Next slide. So before going to Kolkata site. So basically, we are participating in the ALICE CERN project. And as far as India is concerned, we have two major detectors. One is the PMD and MUON arm, which were earlier in the run 2. So we started, participation started in the 1990s. And that time, we, our physicists and then scientists or our teams thought to build detector. So next slide. And during that time only, the grid computing model or concept came from the CERN itself. So in that, as for everyone knows that as architecture-wise, it was started like monarch architecture, where different tiers are there. So in center, there is a tier 0, which is in the CERN. And then there are the tier 1 across the globe. There are presently total 11 tier 1s. And then there is a concept of tier 2 where Kolkata or our tier 2 is situated. So, and we thought in that direction that we will start our center as a tier 2. Next slide. So just as a brief, that my institute name is the VECC, Variable Energy Cyclotron Center. It comes under the Department of Atomic Energy. And then as far as this WLCG, Worldwide LHC Computing Grid concerned, we are nominated as a Kolkata Tier 2, which is for the ALICE experiment. And as per the GOG-DB, this is the nomenclature followed in for this WLCG sites. So that is the name. We have Subhasis Chattopadhyay is our mentor, and then we 2 persons are managing the facility. In the initial days, Tapas Kumar Samanta and Sushant Kumar Paul helped us to establish the centers. Then next slide. So from where we started, I just want to mention that we started the journey in 2002 or in 2003. So means that time we have only the 2 computers, and made the connections between this, and we were connected by very bare minimum network bandwidth to the CERN. Next slide. So this shows that we started with the 2 cores of the machines. Now we have something like 5,000 cores of the computing. So this evolution happens from the 2002, it's desktop machines. Then we have tier tower-like servers. Then 1U server concept came. We procured some 1U concepts. Then there in the 2008, 2009, blade server, blade architecture came into the picture. And there we have procured many blade servers. Then there were means we procured for the Dell also. In 2012, we started about the GPU computing also, and we are doing the research in the field of the GPU computing. And then we procured Geonphi. Now it's not no longer continuing. So we procured Geonphi coprocessors, which has 224 cores of the machines. Then in 2017, it's kind of 48 cores of 48 nodes of the cluster we procured, which has the huge computing cores. And recently we have procured something like 16 Dell node clusters. So altogether we have 5,000 cores of the computing. Next slide. So this picture, I mean, as far as this ALICE experiment is concerned, they have a very beautiful Mona Lisa web page by which you can monitor the site status and daily up and downs. So I like that, and every morning we came and then we used to have the look on that. So it shows that how evaluation of our site with respect to the number of jobs running on the ALICE, running for the ALICE, or number of jobs. So first picture shows in the 2007, we have something like bare minimum 14 number of cores. Then in 2009, we have procured new installation, new infrastructure, and that time the computing element changed. So our site was something like two pictures in that graph. Then in 2010, we have full-fledged LCGC, And in the 2013 onwards, we were running with the cream C, and in the subsequent site, I will mention that we now switched to the HT Condor. So next slide. Yeah, similarly, with respect to the storage is concerned, we started, and yeah, this slide. Thank you. So with respect to the storage, we also started with something like 500 megabyte of disks. Nowadays it's nothing, and now presently we have 5,000 terabyte of disk. So we procured, means in the desktop machines there were something like 512 GB MB of the disk. Then slowly we started increasing the spindles. That then came something around in 2006 that NAS box comes into the pictures, network storage, and then we procured that. Then it's kind of efficient SAN based storage came into the picture, and we also procured IBM storage of the 200 terabyte in 2011. Thereafter, it's each spindle disk size is so huge, and now these days it comes one disk as a 10 to 12 terabytes or higher. So we thought and then changed the plan of going to the SAN based storage to the disk based storage solutions. So I will subsequently in slide I will mention that. So we from 2015 onwards we procured disk based low cost disk based storage servers only, and by accumulating that, presently we have 5 petabyte of the storage. So these all it kind of shows that piece by piece we have built the infrastructure and come to the today's stage. Next slide. So this one more major point as far as any computing center is concerned, that you have to manage the infrastructures, and then when you bit by bit increase the infrastructure, you don't think the auxiliary cooling and power. So this picture shows that in 2006 we have some few racks, then we increased and we have blade servers kind of infrastructure. In 2010 we are kind of full of the servers happened in the entire lab, and we could not sustain with the cooling. So therefore we changed over the cooling solution, and in 2012 onwards we pushed implemented a cold aisle containment kind of cooling solution, which is running till now and satisfactorily. So I will show you this the picture. Next slide. So this shows that what was the concept behind this cold aisle containment. So I must say that this is an efficient cooling solution as far as the Indian perspective or our Asian environment is concerned. So what we are doing is that we are trying to contain the entire cold air in the zone of IT equipments only. So in the top picture, you may say that this is showing the flow diagram of the air. So in the left-hand side, it is showing that we have precision air conditioners, which throw the precision cold air below the false flooring. And then this cold air is confinedly provided into the IT zone, which is shown in this below picture, that only in that we are providing this cold air, and this cold air is sucked by these all the IT equipments. These means sucked from the front and then throw from the back. So and then hot air is circulated again inside the room, and then this circulation takes place. So here temperature gradient between the cold and hot zone is only 5 degrees centigrade we are maintaining. So which provides the efficiency with respect to this power utilization effectiveness. This is kind of a factor by which you can measure that any computing center is good, means power efficient or not. So how much total power you require to run the your facility, and then how much power is required only for the computing infrastructure. So we could achieve something like 1.4 factor of this PUE, which was earlier factor 2. So this in 2012 we implemented, and this is running till now. So next slide. So with respect to any infrastructure, I talked about the computing cores, I talked about the storage. So now there is the main big player, whenever we call it, is the for the international projects for where network bandwidth is the major concern. So we started with something like 120 kbps of the shared link in 2002. Then it was increased to 2 mbps, 4 mbps. We procured from the different network provider, Bharti, Reliance. Then we have a government, earlier it's kind of ARNET. From the ARNET, we procured something 100 mbps in 2009. And in the 2011, 10-11, NCAN comes into the picture. So NCAN is the National Knowledge Network, which provides now consistently network to across India or Indian universities and the Indian institutes as according to their the need. So from 2003 to 11, we have 300 megabits per second of the speed. Then they upgraded to the 1 gigabit per second in 2012. In 2017, we have 10 Gbps. And now recently, this is kind of saturated. So we are upgrading to, means NCAN is upgrading to 20 Gbps. They are presently upgrading the link between the international link from Amsterdam to Geneva. And then means internally, they have dark core fibers, so which is providing 2 path of the 10 Gbps. So our site and our infrastructure will also be upgraded to the 20 Gbps of the network speed. Next slide. So this is kind of, I just want to capture of our journey from 2002 or 2007, when this Mona Lisa picture came into the Mona Lisa monitoring came into the picture. So from 2017 to 2021, we have completed something like 15 million ALICE jobs. ALICE says that they have some benchmarking tool where each and every job is something around 10 to 12 hours or 12 to 14 hours of each job. And those are running consistently from last 15 years. And we can say that there are many up and downs, but we achieved quite a good amount of the computing jobs. And we are 24/7 operational, and our availability is also more than 90%. And now these days, we are now AMC or maintenance cost to manage over the site, because this means maintenance AMC cost or is higher than the procuring the new infrastructure. So therefore, we try to discard the older infrastructure as much as we use them, and then we procure the new one. Next slide. Yeah, so this is again just a picture which shows that yeah, we in India, VCC Kolkata is connected, and these lines shows that how the network traffic is going on between the different international tier 2 means ALICE sites. So next slide. So here we in 2017, when we procured 48 node cluster, that was listed in our top supercomputer list of in India, and this is still in the top supercomputer list. We achieved something like 51 teraflop that time. Next slide. I just run faster. So this shows the evolution of our grid computing facility from 2002 to 2022. So how bit by bit we procure the different type of infrastructures, and what are the things we are doing. Next slide. So as far as ALICE experiment is concerned, Kolkata tier 2 is the only tier 2 in India, and then this is providing the computing resources according to the M&OA share to the ALICE. And means I can say that with this efficient and green and efficient cooling solution, this is our one of the achievement. And next slide. So we have a tier 3 cluster also, which is not part of WLCG, but it is providing the computing infrastructure across India to the different universities, which are the collaborators, and we are participating in different experiments like STAR, Alice, CBM. We have medical imaging facility. There also we are, our computing infrastructure has been used. I want to mention that due to this grid or our Kolkata Tier 2 IGCA, Indian Grid Certification Authority, is also developed, which provide the grid certificate to all the users across India, and all the hosts, which are the host servers. So they are providing the host certificate or grid certificate to this. And due to this due to our collaboration between the international high-speed network infrastructure also developed in India, and NCAN is the great achievement. So next slide. So in just I will mention that as I mentioned that we are now focusing on the disk-based storage solutions, where we procure bare minimum metal with the multiple number of disks. So this upper picture shows that we procure something like 8 servers with 16 or n number of the disks, and across the servers we make a group of the disks, which is called as the RAIN, which is the redundant array of independent nodes, which will increase the reliability of the storage solution. So if entire one server fails, then also total storage solution or storage is up and live. So next slide.
Yes, because we have 2 minutes left.
Okay, so I will just finish it. So this is over the small tier 3 cluster. Next slide. This I just want to mention that as far as this Asia Pacific conference, so these are the ALICE sites in across the Asia, which are the participating for the ALICE experiment. Next slide. And this is a long journey. I will not mention this how we achieve. So this is a day by day configuration. So next slide. Here I just want to mention that as far as outside world or any experiment site looks, that it should have computing element and then storage element, and beside the computing element there are some worker nodes or computing nodes are running, and beside the storage element there are many disks and those are running. But it is not as simple this. Go to the next slide. It's when you manage computing farm or computing infrastructure, then your entire site is like a zoo, because in the right panel we have shown that different type of servers. You have 1U, 4U, 2U, and then for the right hand side you have all the services running on that. So next slide. So this is something like end of my talk, that we started and then now we in 2016 onwards we started for concentrating our efforts in the heterogeneous computing. So there we procured this GPU and Xeon Phi servers. So we are doing the research based on the different available number of processors and architecture for computing in the market, and to utilize those. So presently we have utilized these infrastructure for the new CBM experiment. So and this and as far as the ALICE is concerned, we will provide the infrastructure, necessary infrastructure as per Amendoe share rule. So next slide. So network, I must thank to the NCAN India, who is providing the network facility and across the India, and then they are upgrading as according to our the requirement. Thank you.
Okay, thank you. The FICAS is presenting. And the session 1 is close time is 10:30 and almost finished. Thank you again for all presenters. And the 30 minutes later, we have this session 2 and start again. And thank you for your participant and the presentation. Thank you.
Thank you.
And, Andrew.
Yeah, how's it going?
Yeah, Andrew, and I move to the Bernard slot is session to last slot.
Okay,
And
not a problem.
yeah, I sent a mail to him. Okay. See you
Cool.
after 30 minutes.
Okay.
Bye. Vikas, are you there?
Yes, I just want to know, is the slides and agendas is available, means slides of the different participants is available on the agenda page?
Yes, pardon?
Presentation of different participants
Yeah.
available on,
I'm not sure.
okay. So
Anyway.
means, is there any
Anyway.
way to access the presentations of the other participants?
We'll need to upload those into Hoover. And then you should be able to access it from there. Vikas, did you catch that?
Pardon? I could not understand.
The presentations can be uploaded into Hoover, so we just need to do that.
Yes, yes. All materials is upload. Will be uploaded is Hoover site. As you can reference the download. And I will let you know after today's sessions. And
Okay.
thank you, because the presentation contents is very the close relation in the KISTI, because the last slides is some of your maps is described as a link between you and the Korea KISTI and GSDC Center, and they also the tier centers in Korea and from the Sun in Switzerland. So the APRP working group is support for those the scientific areas to the data, big data transfer so fast. So I want to continuously communication with you and the information, sharing information about that.
Yeah, means I could not mention that in the slides. I have mentioned that there we have started ATCF. See, ATCF is Asia Tier Center Forum, so which is basically collaboration between the KISTI and Asian participants.
Okay, you have a contact point in KISTI?
Yeah, his name is. I can share the. I cannot mention it. Sorry.
Tonori, yes. Yes, the GSDC center is very familiar with my center. So we are the same technology based on this high performance networking areas. So yes, it's I guess, and I expect to the deeply communication with you in the future. So
sure. In 2015, I visited KISTI.
Yeah, thank you again. And if you're possible in the attend the next session too, and we will talk more.
Sure. I will join them.
Okay, see you later.
So I'd like to start by opening up our second session. First of all, I'll be speaking about an introduction to our NCI Niren Cloud. Then we'll hand over to Asif Khan for an introduction to bioscience and ASTM update. Then on to Wontak Hong, Science IoT over to Science DMZ, and then Bernard C from NSCC Singapore with an APRP Singapore update and DMC update. And then back over to Jong-Hoon for our final closing remarks. Let's see if I can get this to go into full screen.
Wait a minute, Andrew.
It's better.
Yes,
so I'd like to start.
Hi.
Sorry, can you hear me okay?
Yes, your schedule table is different original. So
sorry.
Yes, the first is from NCI, the second Asif Khan, the third is not Wontak Hong. He is Kyu Kim.
It's me.
Yes, Kyu Kim. And the fourth presenter is Asif Raja from Pakistan. He changed.
Could you just email that and I'll just update my slide,
Yes.
my slide deck as we go.
Yes, and the fifth is Bernard C. Okay, I will text to you from the chatting window.
Okay.
Go ahead.
Cool. So I'd like to speak to you today about NIRN, which is NCI's High Performance Research Cloud. First of all, I'd like to acknowledge the traditional elders on whose land we meet and pay our respect to both elders past, present and emerging. The artwork you can see here is our artwork we produced for our Gaudi supercomputer. We have recently launched our new cloud. Well, it's a cloud we've been running for a couple of years, but we've finally got a name for it. We've called it NIRN. The NIRN artwork was created by Anthony Best, a local Indigenous artist in Canberra.
Andrew, we're not.
Andrew, sorry, the slide's not moving.
How's that now?
Same. Maybe you want to stop sharing and then start again.
Just, yeah, let me stop and restart. Sorry, new computer, and looks like Keynote has crashed. Are you getting video now?
Loading. Yep.
Is that moving now?
Yeah.
Yes, it's
Cool.
moving.
So the NIRN artwork has significance. NIRN is the term for edge in the First Nations Wiradjuri language. The Wiradjuri people live in an area just north of the Australian Capital Territory. The NIRN artwork that you can see shows lines of communication, meeting at gathering places represented by the circular features. And then the arch shapes represent each of the scientific communities researching in the NIRN cloud, surrounded by their data. NCI, like many, well, like a lot of you, is deeply connected into the national research and education networks which span the globe. And we're well served with multiple 100 gig connections running into the facility. What is NCI? The NCI is a national computational infrastructure. We're world-class high-end supercomputer and data services. We're a national tier 1 facility in Australia that enables high-performance computing, data storage and services, and we host national data sets for curation and provisioning. We support over 8,000 Australian researchers across 44,500 unique users of data services. We're Australia's fastest research supercomputer, clocking in at 9.26 petaflops. And when we debuted, we were number 24 in the top 500. The Gaudi system is over 7 times faster than its predecessor, Rygen. NCI is funded primarily through the Australian federal government under a program called NCRIS, which is the National Collaboration Research Infrastructure Strategy. And we also receive funding directly from our government partners and government agencies, the Bureau of Meteorology, Geoscience Australia, and CSIRO, the Commonwealth Scientific and Industrial Research Organisation. We support the entire spectrum of science, ranging from fundamental through strategic, applied, and industry-based. This slide gives some more detail on our funding, our major collaborators, which are the University of New South Wales, other universities in Australia, and we also have some commercial partners who use our facility in a number of different ways. So there are two Tier 1 HPC facilities in Australia, NCI on the East Coast with our Gardi supercomputer, and Perth on the West Coast with their new supercomputer, which I have a slide on a bit later. Both centres provide supercomputing, cloud, data analysis, and community outreach and training. So Gardi is 155,000 CPU cores, 576 terabytes of memory, and 640 GPUs. It's built from 3,074 nodes containing two 24-core Intel scalable Cascade Lake processors and 192 gigs of memory. We also have 50 nodes, each offering 1.5 terabytes of Intel Optane DC permanent memory, and 160 nodes containing NVIDIA V100 GPUs and 24-core Intel scalable Cascade Lake processors. Linking the storage system to Gardi is a Mellanox technology HDR InfiniBand interconnect fabric set up in a Dragonfly topology, which is running at 200 gigabits per second. The storage subsystems are NetApp enterprise class storage arrays linked together in a DD Elastic parallel file system. Like many of you, we also use Altair's PBS Pro for job scheduling. And Gardi has transitioned to using Rocky Linux from CentOS, and that was quite successful for us. Pawsey's new supercomputer is also a 50 petaflop machine with around 200,000 AMD CPU cores and 750 AMD GPUs with 548 terabytes of memory. And this is 10 times more energy efficient than their previous Magnus system. Their new system is called Photonics. Like everyone else in the world, we've been significantly impacted with supply chain issues in Australia. So phase 1 is operational, with additional phases being delivered progressively. Onto our Niren Cloud. We have a program in Australia called Remade in Australia. One of the things we're trying to do is to make best use of technology that we can, and to rebuild things into new and repurposed capabilities. So we repurposed Rygen, which was our former supercomputer, into the NCI Niren Cloud. This is OpenStack based, occupies 22 racks of 72 nodes in each rack, is distributed across 2 data centers. One that is the difference between our data centers is the amount of available UPS power that we have. Our primary data center hosts 1,440 Intel Broadwell cores. This is our primarily our presentation data center. Our secondary data center holds 42,000 Intel Sandy Bridge cores, cut with a roughly 200 terabytes of memory. We also have 4 Intel Optane nodes with 3.6 terabytes of memory each, and around 80 K80 GPUs. We operate 6 petabytes of operational Ceph storage, which we use for volumes, CephFS, block storage, and S3. Most excitingly, we have an additional 12.5 petabytes of Ceph being delivered next week. We're just trying to make enough space available to install that in our data center. We use a combination of 100 gig and 56 gig Ethernet interconnect. As I mentioned, we're somewhat power constrained on UPS in our secondary data center, which has our largest cloud capability. So we use a model of dispatchability. like energy, where we're able to spin up, power up and down nodes as required. We typically start spinning up in the morning around 7 o'clock to handle the peak workload during the day, and then progressively spin down and power down using live migration to evacuate nodes and to compact the workload around 8 or 9 at night. Pawsey also has a cloud called Nimbus, which is also OpenStack based. They're currently working on a more recent technology platform than us with 3,700 AMD cores and 58 terabytes of RAM. They also have around 9 petabytes of volume storage with 12 NVIDIA V100 GPU nodes and 100 gig Ethernet network. Like all of us, we've had to respond to COVID-19, and both Pawsey and NCI were quick to make our facilities available for researchers to perform necessary COVID-19 research, to store genomic sequences, to perform alignment and other activities. We rapidly pivoted within about a week or so to announce an accelerated access initiative. We onboarded researchers extremely rapidly. We offered around 20 million service units on our Gaudi supercomputer and around 0.5 petabyte of storage. We also provided cloud resources as requested. This has been remarkably successful and appreciated by our research community on COVID and our National Health Department. So as I mentioned, our COVID-19 response was processing and analysis of genome sequences, mathematical modeling of vector stages and predicting transmission and containment, computational predictions of protein structures associated with COVID-19 and associated biomolecular modeling, which was extremely important as we've run through multiple COVID variants. Modeling the economics of the COVID-19 global pandemic, using it for population mapping and demographics, assisting with global biosecurity, and performing domestic epidemiological modeling. COVID-19 also presented us with a number of operational challenges. Australia had a very strict isolation and quarantine policy, and many of our state borders were locked down until only very recently. We wanted to manage staff workload, safety, and well-being. I can see I've made a spelling error on that. Fortunately, the majority of NCI staff were already equipped to work remotely. We've relied on Slack, Zoom, and other collaboration platforms, which we already had implemented. We upgraded people's remote workplaces where necessary, but we've faced challenges of maintaining staff motivation due to stress and well-being. And we also had a requirement for only essential staff to be on site. This required extreme social distancing, check-in and check-out, and limited numbers in the data center, which has impacted a number of system deliveries and maintenance capabilities that we would normally have planned. So just to give you an idea about where we're located on the Australian continent, NCI is inland in our capital city of Canberra, and Pawsey is on the west coast. We're connected with 3 pairs of 100 gig network services. Only the oceanic service is shown, but there are 2 fibers running terrestrially and a 3rd fiber for Triversity, which is sea-based. One of the things I was very proud to be associated with was to be a member of a multidisciplinary team formed by NCI, the Australian National University, and the ACT Department of Health to fast-track contact tracing systems, build disease spread heat maps, look at hospital demand forecasting, and provide visualization and data analytics. We were able to have this service operating less than 1 hour after the initial request, and we used an open source development model where all of the participants shared. You can watch the HPC COVID-19 Australia Response Showcase at the link below if you're interested in doing so. We also participate in a number of national projects, including Galaxy Australia. Galaxy is a genome sequencing platform. We're honoured to be part of building a personalised dynamic consent system for genome processing with the National Centre for Indigenous Genomics. We're about to launch what we're calling Australian Research Environments, which is based on Open On Demand. And we're working with ARCOS, which is a national containerization facility, which will be providing curated container storage. We're also investigating how best to manage the singularity containers that are becoming more and more popular within our environment. So the Australian Research Environment and Australian Research Container Orchestration Services will combine the ARNet Cloud, NCI's Niren Cloud, and the Pawsey Cloud into a single Australian research environment. This is based on a product called Open On Demand, provided by or developed by Ohio State University. It also has a plugin component for Globus, which is a very widely used file transfer system. And as I mentioned, we will be using curated containers for identified workflows, optimized toolkits to produce reproducible science, and building on a national Docker registry. So our Open On Demand Australian Research Environments, as I mentioned, Open On Demand is developed by Ohio Supercomputer Centre. It's an initiative which is an innovative and interactive interface to remote computing resources. It allows any user with a web browser to access resources at NCI. Really makes it easy for new users to come on board. We're able to offer a range of remote computing resources faster and more efficiently. It has a graphical user interface for Jupyter notebooks and virtual desktops, uses Globus for data transfers, and we've also augmented it with a rich application portfolio based on our 10 years of virtual laboratory experience. We started a technology preview to around 1,000 users in 2021, which has been remarkably successful. And we're building the fully integrated platform. We're still running a few months behind on that. So it'll be a plug-in free web experience with easy file management, command line shell access, job management and monitoring across different resource managers, a graphical desktop environment and desktop applications, supporting RStudio, Jupyter, Dask, ParaView, and a rich range of applications. So that concludes my presentation. Just let me check the chat notes. And I'd like to now hand over to Professor Asif Khan from Padana, who will be providing an update on ASEM and an introduction to bioscience. Over to you, Asif.
Thank you, Howard. Let me share my screen. Okay. All right. Thank you, Jung-Hoon, for inviting me to be part of this, and thank you, Howard, for that handover. And a warm welcome to everyone from Istanbul. So actually, there was a typo in the title. So it's not ASIN, but ASEAN Update and HPC for Bioscience. I've been part of the APRP working group since its first establishment when it got started in 2018 in Singapore. And we have been doing this on a regular basis. So I usually update the ASEAN part, and then of late, I think since last year, Jung-Hoon has asked me to provide some update on how HPC is being utilized for life sciences or biosciences. Pardon my voice, a little throaty there. So here's a bit of a history. It's always good to recap when, how we started. So this started actually at SC Asia, Supercomputing Asia 2018 in Singapore. And that's when we got, we had APAN53 co-locating with SC Asia 2018. So the first APRP was then we have been having without a miss over the years. So it's been this is the 5th year now. So we are having, this is 5th year and the 9th APRP at APAN53 in Bangladesh. And the first one that we had, we actually had some funding support from TNCC, and we were able to invite quite a number of notable participants from ASEAN member countries, and we had a good participation and good discussion, and these are those who are present. And this is just a reminder that hopefully we'll be able to bring these people back someday when the dream of ASEAN HPC is realized, hopefully soon. The motivation of focusing on ASEAN HPC was because ASEAN, to some extent, to a large extent, is actually a little behind from other regions where HPC is quite well prominent, established in terms of not just familiarity of the researchers, but in terms of the infrastructure. So the key objective was to promote a vibrant and relevant HPC ecosystem in ASEAN, and there was also a proposal to set up an ASEAN HPC task force, to set up an ASEAN HPC shared facility, and to establish that an HPC task force by ASEAN was set up in 2018, and they have been discussing, deliberating on how to move forward in this direction. These are actually updates from the last APRP meeting. I've not received any recent updates. Perhaps I think Yves from the participants could share more later, or maybe as part of the general update or discussion later. But as of the last APRP meeting, this is what we had as the update, that they're looking at a sharing infrastructure model, and collaboration, of course, is not restricted within the region. They're open to outside the region. And of course, this will open to a global HPC resource. And but while that is work in progress, I think there's a lot of emphasis on growing the human capacity to actually utilize a resource like that. And as part of that, there is collaboration that has been, I think, explored or is already ongoing with RIKEN's Center for Computational Science, RCCS, home to FUKAGU. So, and as part of that collaboration, I think the discussion appears to be that the shared facility would be somehow routed through FUKAGU's and the supercomputer at that center. That's as per my understanding based on the update that I received. The near-term objective is to establish the inaugural ASEAN shared facility on Fugaku, and also to initiate HPC courses as part of the training, especially the younger generation. And this EU ASEAN HPC initiative is necessary to bring more of these cross-continent collaboration and to continue upgrading the younger generation to become more familiar in terms of utilizing HPC. So they had this HPC school. They had a successful one last year, and there's plan to have a second one. So second EU ASEAN HPC computing school has been announced, and this will be held sometime this year, and more details will be followed. Separately, we also have other HPC initiatives led by, for example, this HPC AI Advisory Council in collaboration with National Supercomputing Center of Singapore. They have this so far. I think this is a regular competition. They had last year one. I was part of that, and we sent some teams from ASEAN, and it went quite well. I think there was a lot of sharing of knowledge, and there was a lot of exposure, again, especially with the younger generation. And these are the this is the announcement for this year's competition. So they're doing the same one for this year, and these are the winners from last year. And we can see, although it's dominated, I think, by China, Taiwan, we do have a mention here, University Putra Malaysia. From ASEAN, and of course, I think there's also from Singapore, Nanyang Technological University of Singapore. So we do have some presence from ASEAN at these international competitions. So that's I think much desired. There's much needed, and there's much more to be desired in more of these participations. So we thank HPC Asia Council for taking championing these efforts. Separately, of course, there are notable conferences. So we have HPC Asia 2022 that has concluded supposedly from January, and Supercomputing Asia, I think, just recently closed March 1 to 3, and there's an upcoming Supercomputing 22 in November this year. And so before I shift gear to the bioscience talk, well, we are now in the 5th year as per the conversation about a shared or an ASEAN HPC. So we still, as a user, in the ASEAN region, I still have not seen or realized the benefit of this. We hope, we'll get to that dream reality of having access to an ASEAN HPC very soon, so it could benefit many researchers in ASEAN who are looking forward to a resource like that. And I think this will be a great enabler in them being able to ask important questions that could be, facilitated by such a resource. So for the audience, I just want to very quickly, share with you some aspects of bioscience where HPC, could be much needed. And bioscience, in many ways, is the HPC aspect of bioscience, could be loosely termed as bioinformatics. So bioinformatics is a discipline, is an approach or a discipline that utilizes informatics in terms of solving biological problems. So here's an operational definition of bioinformatics: is the development and application of techniques from computer science, mathematics, and statistics to address biological problems. And as part of that, of course, we need as much compute as possible because biological data is growing. And down here we have the philosophical definition. It's basically looking at information content and information flow in biological systems and processes. Essentially, we are looking at biology from the lens of information theory. And again, since we are talking about information theory, computer science, all the HPC and etc., all become more and more relevant in terms of effectively studying biology. And we could break it down into 4 components, or 2 main components: data warehousing and data mining. Essentially, that's what bioinformatics is all about. So you have your biological data at this part here. So there are just so many different types of biological data. Then you have genomics, proteomics, lipidomics, metabolomics, all kinds of omics, the complete set of all different biological molecules. And these are stored in databases for various reasons, so it's organized and we can quickly fetch what we are looking for. We don't waste time. And algorithms are used to study them, they're built to study them, and then the results of those algorithms are presented for making sense of what has happened, what have we learned as an output of that algorithm. So it's not that So it's easy to remember this: data warehousing, data mining. Essentially, that's bioinformatics, and bioinformatics has actually underpinned integrative biology or bioscience or life science, you may want to call it, to handle the complexity of biological data. And this is across various dimensions. From one dimension, which would be your sequencing of the genome, which is so-called the letters or the ATGC. And you have two-dimension in interactomics, where you look at the interaction between molecules and you identify hub genes or proteins that are playing a very important role. And if there's a mutation or some deletion in these, it would actually affect so many, and diseases can happen. So it allows us to identify these key players. And of course, we can look at 3D structures of proteins. Proteins are not just a bunch of letters, 20 amino acid letters, but they actually have a shape, although they don't have colors, but it allows us to visualize how they look. And of course, and even it goes all the way even to 6 dimensions through bioimaging. So bioinformatics spans through all these, dimensions, and it's critical in the understanding of biology. So for every experimental observation out there in the lab, there is now like an equivalent computational or informational aspect of that is working hand in hand to basically expedite or catalyze the experimental research work. So in summary, bioinformatics is key, is very important in moving biological research, bioscience research forward. And to do that, we need a systematic approach, a systematic data warehousing approach, and we deal with data. Data can be big, so we have to, retrieve the data, clean the data, integrate the data, annotate, build the database, and worry about updating the database from time to time so it doesn't become obsolete. And then data mining. So it's not just straight away data mining. You get the data and you mine it, but you actually have to go through a workflow in order to make sure that it's not garbage in and garbage out, and this itself takes a lot of time and requires a lot of infrastructure to support us. And it is I'm not sure if you've seen this, but it is said that this paper was published, and it said that by 2025 this is the projected annual storage of data. And the big wigs, for example, Twitter, astronomy, YouTube would no longer be the biggest or the big data producers. Well, they will remain as big data producers, but the biggest one by then would be genomics, and this is driven by. It's going to be driven by personal genomics, because the prices of sequencing your genome is going to go lower and lower. I'm going to show you something there. And if we consider healthcare data, it's going to be even bigger. So genomics or healthcare data is going to be one of the biggest producers of data. And again, when you have so much data, there is need for HPC to crunch that, not just to crunch brute force, but to really come up with smart algorithms to parallelize many of these tasks. We just don't want to do brute force. We also want to make sure that the tools that people are building are actually ready to take advantage and in a smart fashion. And just this is something I guess all of you should be familiar with, just to remind us what petabyte as a scale is actually 10 to the power of 15. And of course, I think we are already into exabyte and zettabyte in terms of the global data. But in terms of biological data, you must be wondering, how big it is. So this is actually statistics from the European Bioinformatics Institute. So they are currently at 390 petabytes of raw storage, and we are still in 2022. So in 3 years time to come, and with personal genomics, hopefully, taking, becoming commodity with the prices going down, more and more people will be sequencing, and there will be tons of more data for us to manage. And this is just demonstrating that the drop in the price. It took us $3 billion just to sequence the first draft, and the prices were still very high in 2000 when the Human Genome Draft was announced, and the 2007 prices really dropped because of economies of scale and the competition and the development of next generation sequencing, and the prices have actually been dropping since then. Around 2014, we overcame this challenge of trying to bring down the price to lower than 1,000. And we are looking towards 2025 around 100, and beyond that even cheaper than 100. At the moment, I've not heard of anyone actually paying 100 for a whole genome, but around 400 to 500, it's already a reality. And I think it's just going to go even lower. And of course, if you are one of the biggest clients of Illumina, probably you could maybe negotiate 100, but this is not open to everybody. But in general, I think 400, 500, 600 it's becoming kind of a norm. So it's really cheap. It's almost buying like an iPhone, and if people can buy an iPhone at that kind of a price, I think this. The barrier to thinking about sequencing your genome, it's kind of somewhat removed, and it just becomes more accessible to people. There are companies already offering these services. And so genomics is already inside, can be considered big data. It satisfies all the 10 V's, not just 3, but 10 V's of big data. And just to give you that demonstration, a whole exome sequencing can be done in just 5 minutes. A whole genome sequencing can now be done in less than 1 hour. These are statistics from 2018. I mean, these numbers are from 2018. Today, I'm sure it's much faster. So just imagine how much how many genomes they must be churning out with that kind of speed. And so to move from data to knowledge, of course, we need to have the algorithms, visualization, but I think what the picture didn't show is the infrastructure to support all that in order for all that to happen. And I think, more and more as we deal with the big data, we realize how these are critical. I personally have, had a student project where just with whatever little we had, we estimated a project to take 7 months for a master student just to get the results of analysis. And something like that should not be the case. We should be able to use and get results very quickly. And that was just, not that big of a data. Imagine for much bigger data. So, I mean, those of us in ASEAN, are we really hoping that, this would be, HPC would be omnipresent and it would be easily accessible for us to really take advantage. And, you probably have heard of precision medicine. And this is another exciting area where genomics is going to make a big difference, where medicine will be algorithm-based and data, AI, AI will be utilized to learn the data and come up with some really great, findings, discoveries that can help improve our health. Here's actually a schema of how precision medicine would actually kind of take place. And in some parts of the world, this is already happening. So you actually have multidimensional molecular profiling, sequencing, mRNA profiling, genotyping, microRNA, epigenomics, proteomics, all the omics are here. And then on the other hand, you get experimental data from hospitals, you have clinical and pathological data, all being integrated in this major resource. And this is where storage, processing, annotation, all that happens. And then and once that's settled, then data mining can take place. And so we really need people with skills in bioinformatics, and of course also skills in utilizing HPC, understanding parallel processing, parallel compute. So that training, is really very minimal at the moment. It's not even part of the curriculum of many programs. So again, there's much to be desired, much to be done to really get us to start even, having a human capital to be able to support something like this. And this is just an example of the very many tools that would be required to pull off something like this. So really, multidisciplinary and interdisciplinary effort or initiative in order to really reap the fruits of that labor. So I hope you got a sense of some idea of how bioscience is shaping up, evolving, growing, and how bioinformatics is facilitating that, and the need for HPC in order to really for us to leapfrog to make that next big jump. Thank you very much.
Thank you, Asif.
That's it. Back to you, Andrew.
Fascinating presentation.
Thank you.
Does anyone have any questions for Asif? Maybe I could throw you one.
Sure.
With the evolution of new sequencer systems, particularly the Oxford Nanopore system, the amount of data coming out of that seems to be significantly larger and based on an electrical output rather than just a direct sequence output. Do you see that that will have an impact on genome processing going forward?
Yeah, thank you for that question. I think in many ways, Illumina still kind of somewhat dominates. So I think for most people, that would still be what they would be dealing with in general, for at least for some time to come. But some of these new technologies are really exciting, and they're coming up with new approaches, new ways. So in terms of data, I think it would change to some extent, and we really need to also look into tools to kind of accompany those developments. There are a few groups that are looking into that, and there's just so much that's actually going at that front. So I'm not really sure how that would actually impact the masses. I think Illumina has quite a solid grip at the moment, but yeah, I think there will be some effect to that, and the technology would have to follow. But also, I think the other thing is in terms of the accuracy, there are still some kinks to be sorted out before those really become mainstream application, or it's utilized by many out there.
That sounds very similar to the way we're approaching it in Australia. So thank you for that update.
Thank you.
We may move on to our next speaker, Gil Kim from KISTI, who will be talking to us about Science IoT over the Science DMZ. Over to you, Gil.
Okay. Can you see this page?
Yep, we can see you just fine.
Yeah. Okay. Hello, everyone. I am Gil Kim, working at KISTI. I am very glad to present my work here today. The topic for my presentation is Science IoT project of KISTI. The name Science IoT refers to collecting scientific data using IoT network. First, I would like to introduce the Science IoT, focusing on its use cases. And next, I explain our relationship with the Science DMZ-based research platform and finish the presentation. Okay, now start. First of all, let me explain why we started the IoT project. As you know, IoT is one of core technologies in many next generation industries, and as IoT spreads rapidly, the number of IoT devices and the data generated from them is also increasing. The most developed countries have already recognized the importance of the IoT technology, and they are implementing plans to establish IoT infrastructure and services like this. This rapid growth of IoT enables the development of new services, not only in industrial areas, but also in academic, public sectors, and particularly scientific field. Furthermore, the research paradigm is changing from theoretical and experimental research to data-oriented research. So there are gradually increasing requests for wireless network services from the CREONET users, our users. So with this increasing needs, we decided to include wireless IoT network service by expanding the service scope of our CREONet. To meet the expectations of R&D on IoT infrastructures for science applications, we have launched the wireless IoT network called Science IoT, based on low power and wide area network technology. We build and utilize IoT network infrastructure for wireless network data transmission, especially for science researchers and public purpose. We provided customized IoT infrastructure and data services to several demanding organizations. Here are the use cases so far, this table. And from 2018 to 2019, we deployed Science IoT infrastructure for monitoring environmental radiation and reveal the data to the public in real time. There is first one. And in 2020, we built a safety management system for underground laboratory, and it collects the real-time location information of underground workers, so it enabled them respond quickly in emergency situations. In addition, we have established the Science IoT infrastructure for research and education in research institutes and some university campuses. So students will be able to make use of Science IoT for their research and develop their own services. And last one, in 2021, we designed the IoT network providing remote water metering service for Daejeon City. We also constantly making technical upgrades to the IoT hardware and software platform to satisfy various requirements of each user. We connect our data storage to the Science DMG-based research platform, so the research platform users can utilize our collected data for their AI computing. From now on, I'll introduce 3 of these use cases one by one. As the first use case, Science IoT was deployed to support the IRNet for environmental radiation monitoring. The IRNet, operated and managed by KINS. KINS is some organization in Korea, and it is an automated surveillance network for efficiently monitoring environmental radiation in Korea. It collects and monitors environmental radiation data in hundreds of sites in Korea and shows the information to public, like this slide. As you can see, the first figure, the IRNet was facing stability problems before, such as quality of service due to aging 2G network infrastructures, and it was vulnerable to security and in the transmission of radiation data due to the use of commercial internet network. So therefore, their existing infrastructure cannot guarantee safe and reliable data transmission of radiation data. So Science IoT replaces the wireless communication with LoRa technology. And we also provide CREONet network enables reliable and secure radiation data transmission as shown in the second figure. This slide shows the Science IoT network architecture for the IRNet. The collected data are transmitted to the LoRa device to LoRa gateways. And the gateways send the data to the network server through CreoNet. And finally, the packets are sent to an IRNet service server. In doing so, Science IoT makes reliable and safe transmission possible without mobile network providers. We use best LoRa technology to provide higher data rate than general LoRa communication. And now this type of Science IoT sites has been built in 20 regions in Korea, and their data are stably provided to KINS. This is our IoT management interface for this type of Science IoT. And as for another use case, in 2020, we built safety management system in underground spaces. The underground lab called Yemi Lab is located 1 kilometer deep from the ground, as this figure. Researchers are working in the underground lab aiming to search dark matters. So there are many research facilities for searching dark matters in this underground lab. Under this situation, when an accident occurs, it is difficult to cope with the accident. It is very important to locate researchers for the purpose of their safety. However, because GPS, the global positioning system, is not available in the underground facility, it is essential to develop indoor localization system without GPS. So we developed this using LoRa and BLE Bluetooth with low energy technologies. There are 3 devices in the developed system. A worker carries the first device, number 1, in this figure. It is a wearable BLE tag, and the BLE tag periodically generates a BLE beacon signal. And the second device is a fixed type LoRa and BLE dual communication device. When it is received a BLE beacon from the first device, then the information of corresponding BLE tag is transmitted to the LoRa gateway using LoRa communication. The third device is LoRa gateway. It transmits the data to application server. Then the safety management system is working on these devices. Each fixed type LoRa BLE dual communication device is installed 20 meters away from each other, so the server can notice which one of the fixed devices is nearest to the worker. In this figure, this one is nearest to this man. So, and the server also knows the direction and movement speed of the worker by accumulating and analyzing this location information. Finally, the status and location of the worker is shown on the web interface, our web interface. And the next is project for smart city service. In this project, our technology for IoT network construction and operation management is being used to build IoT networks for public services. In 2021, we carried out an IoT network planning project funded by Daejeon City. The Daejeon is one of the largest cities in Korea, which has a population of about 1.5 million people. And we designed the network structure and development layout to build the IoT network that covers the entire city of Daejeon for remote water metering service. The design result will be applied to the demonstration project in this year. And next, the installation covering the entire city will be made in stages. I would like to introduce the most interesting part of this project. As a part of the IoT network planning, we have to find the appropriate deployment locations of the LoRa APs. With consideration of the location information of all of water metering nodes, and the communication distance and capacity of the LoRa APs. So this is our objective in this project. So we simulated the radio signal propagation using a simulation tool. The simulation tool has a built-in 3D map and can set up communication frequencies and wireless parameters of nodes and APs, and we can set antennas and radio propagation models and other many things. The receiver sensitivity prediction result of a nearby area for a base station in this figure is expressed in color as shown in this. So we can see the radio shadow area in this figure by color. It is influenced by distance from the base station and buildings between the sender and receiver. So we placed APs on the entire map and compared the radio simulation of those APs with the location of the nodes to determine whether there are nodes located in the shadow area. In this figure, there are some nodes in the shadow area. However, unlike other science IoT project we have done earlier, this time we had to deploy hundreds of APs and across a large area, and thus technical research. So we need this simulation. And when you found a node located in the shadow area, we analyzed the nearby terrain and visibility and accordingly made corrections such as moving of AP or placing additional AP. Through these processes, the final IoT network deployment design was derived. While building IoT networks as above, we are also interested in making our collected IoT data available to more researchers. So we connected our data storage to the Science DMG based research platform called RNE Together. our data is stored in file like this way. The collected data is classified by user, device, and date, and they are stored as a CSV format file. Then the files in our storage are linked to the RNA Together research platform. So the users of RNA Together can access our Science IoT files at Jupyter Lab or Nextcloud for their AI processing. And for our next step, we are interested in the additional development of our IoT platform. In particular, since last year, we have been attempting to develop advanced IoT data processing by combining IoT edge computing technology. And of course, we will continue to try to increase use cases of Science IoT. If there are any APRP member who are interested in collecting research data using IoT technology, then I expected that they will be able to cooperate with us. Thank you for listening.
Thank you for a really fascinating presentation. Would you mind stopping screen sharing just so I can see if anyone's got any questions? While we do that, I've got a couple of questions for you. You mentioned you're using LoRa APs for the city implementation project. How are you uplinking those APs back into CreaNet?
Pardon?
Would you like me to repeat?
Yeah, please replay.
So your citywide LoRa access point deployment, how are you connecting those back to CreaNet?
Okay. We connect the LoRa APs to our CreaNet with some of them using the lined CreaNet, and some of them are using the existing network providers network. But we encrypted all the data, so and they are using VPN. So we are logically, we think we are logically, they are logically in CreaNet network.
How are you managing that number of access points when things fail? Do you have a network operations capability to monitor the access points?
Yeah, we always monitor all of the APs, access points, and it is, we cannot manage all of them in many years. So if the service starts, then the organization which use the network will take the management.
And one final question from me. Are you allowing are you allowing public access over your LoRaWAN network?
No, because all of them are developed for very targeted to the demand organization. So we cannot open the existing infrastructures, but we we also making another type of science IoT infrastructure that can open the platform to public.
Excellent. That's some very, very amazing work that you've done there.
Thank you.
Noah, anyone else? Any other questions from anyone? Okay, let's move on to our next speaker, Asif Raza from Sakur BA University in Pakistan. And Asif will be giving us an update on Pakistan and an introduction to AI science. Over to you, Asif.
Yeah, how are you? Thank you, Andrew. Can you see my presentation, PPT?
All good.
Yeah. Okay. So thank you very much for inviting me for this APAN53 and in Bangladesh. So today I'm going to present about, my updates related to the Pakistan and also HPC for AI research, right? So I am Asif Raza, as already introduced by Andrew, and I am currently working as a assistant professor here at Sakur IBA University. And along with that, we are also running a center of excellence for robotics and AI and blockchain, which is called CREB. And I'm working here as a researcher. So first of all, I would like to discuss that how our, universities in Pakistan are connected through a network. So thanks to APAN, because Pakistan Education and Research Network, they are providing the infrastructure through which our all universities are connected with each other for collaborative research, and also they are connecting outside of the Pakistan. Around 228 universities we are connected together, and also colleges and our universities levels are connected. So as far as our institute is concerned, our IBA Sakur IBA University is concerned, it is located here in Sindh province, and we are here. Here you can see Sakur IBA is located here. So PAN is also providing international linkages, means they are collaborating with the international bodies like APAN, APNIC, Asia Connect, TIAN, and all these international bodies, and they are providing the linkage to connect with the internationally and collaborate internationally with other research institutions and universities as well. So this is our connectivity related. And now let's, as I told you that we are here working in a CRAB as a, to work on AI, particularly on AI, robotics and blockchain related things. So now I would like to give an overview that what is the CRAB is and what is the main objectives of CRAB. CRAB is basically as a research lab which is located at Sakur IBA University. And here we are working on robotics, as I told, AI related use cases and blockchain related things. And by using the CRAB, we are supporting our local researchers, our students, our educationists to work in these and do research in these areas like robotics, AI, and the blockchain. And we are also having the objective of producing some patentable research and support our regional and national industries as well. And our main objective, which I am going to discuss here, is basically related to the HPC and science CMG infrastructure. Because in Pakistan, we are lacking, some, you can say, the high performance computing infrastructure, as well as this is a new concept that we are going to establish here in Pakistan, which is called the science CMG based infrastructure. And we are also internationally collaborating. So this is all about, our CRAB. Now let's talk about what we are currently doing here in CRAB for AI related research. As you all know, this is a industry 4.0, and AI is emerging, in this, environment. And particularly in AI, we have so many subfields like deep learning, machine learning, neural networks. And in AI, we are dealing with the big data. So if we make a local infrastructure here at CREB, we already make that local infrastructure. We have small local infrastructure here at CRAB lab at Sakkara University for AI related research. We also required the big data related things. We have to manage the big data. We have to deal with the big data, because whenever we are talking about the AI research, it means we are also dealing with the big data. So to cope up all these things, we required HPC infrastructure, where we have GPUs, CPUs, and multi-core environment, HPC nodes, and HPC cluster as well. So currently we have we set up this this is our data center, small data center at CRAB lab at Sakkara University, and we have some blade servers you can see here. And these blade servers, by using these, we are using 4 blade servers from these blade servers, and we created a HPC cluster for our AI related research locally here in CRAB lab. And we establish the container based technology and the Kubernetes. Like Kim said, we have similar type of but small but similar type of environment. We have at the under layer, we have Kubernetes for container management, and we have Kubeflow for machine learning lifecycle related workloads. So we are managing this local infrastructure. But this is not enough, because whenever we are talking about AI science related research, right? So this infrastructure is not enough. So what can be the solution, what we should have to do? So we plan to contribute in a collaboration with other countries, and we propose a project which is called the distributed HPC for AI. So from Pakistan, from Sakkara University, we collaborated with these other countries like Korea, NCF, Australia, and Malaysia. So we won this project, and we won this grant for building a high bandwidth distributed HPC in Asia Connect call proposal. So we successfully granted this project, and in this project we are going to build a high bandwidth distributed HPC, where we have the huge and large environment for distributed HPC. We can utilize distributed computing, we can utilize the science CMZ, means we can deal with the big data transfer as well, and we have the distributed storage as well here. As already discussed by the speakers about this thing, particularly I'm talking about the use cases that we are going to implement here in this infrastructure for distributed HPC in Pakistan. We are basically working or we will work on this part. Basically, we will work on enhanced algorithms we will implement in this distributed HPC infrastructure. We will implement some AI related algorithms. We will implement some deep learning, machine learning related algorithms, and also some use cases related to the big data transfer. So this is our main objective from Pakistan in this project, that we have to work on some AI related research part, and we have to taste this distributed HPC related to the AI research. So what is our roadmap? If we talk about the roadmap of HPC, distributed HPC and science DMZ roadmap here at CRAB lab, first of all, we would like to have connectivity with these countries like Korea. So we already requested to the PAN, and we are thankful again to them. They are collaborating, and they will provide the connectivity through which we can connect it. Our institute will connect it with the KISTI in this distributed HPC environment, and we will deploy the science DMZ here at Sakkara University. We will deploy the research DTNs, and also we will deploy some perf sonar nodes in future in our data center that I showed you before, right? And related to the algorithms, because I told you our part is mostly related to the AI related algorithms. So we will deploy the machine learning and deep learning related algorithms here on this distributed HPC. We are planning to work on this neural network algorithms related things. So many algorithms we will deploy, like CNN, GAN, and all these things. We will also use some modern approaches for training the data sets, because in AI we have to train the data sets. In machine learning, deep learning, we have to train the data sets. We will use these modern approaches to train the data set, like backpropagation, bootstrapping, and all these things. And we will also use these algorithms like reinforcement, inverse reinforcement, VAE, Markov chain, Monte Carlos algorithms. These all algorithms, and SVM, these all algorithms we are planning to implement on this distributed HPC in future, because these are very important, and we have to also test it how we can implement and deploy these algorithms in a distributed environment where we are connected in distributed way, and how we can transfer the large amount of data as well. So as far as our current project, this is our planning overall, and here we are currently, we have some AI related research projects at Crab Lab. I want to show that those projects, because maybe these projects we will implement in this distributed HPC in future as well. Because our researchers, our students, PhD students are working on these projects, and I want to show these projects as well, currently on which we are working on. Our one project is basically related to the vehicle detection and speed estimation by using the CCTV cameras. So in this project, we basically detect the vehicles on the road and also estimate the speed by using the CCTV camera. So here we use some vehicle classification methods, localization methods, and we use the to detect the vehicles as an object by using the YOLO version 4 framework, and also we use the neural network framework DarkNet, through which we can classify and detect the vehicle on the road. And we also identify by using its identification number. We put identifications numbers on these cars to identify which car is this, because we have to identify as well in this project. And we also have to estimate the speed of car, average speed, maximum, minimum speed as well. So this is the one part, and another part is basically of this project is to same thing, like we have to identify the vehicle, we have to detect the vehicle, and speed estimation by using the drone camera. Here we retrained the vehicle aerial identification data set. We use the this data set to retrain the model. So if you are interested, you can see on these links, and you can see further videos of how these are working. These are just the snapshots. So this is the one project on which our researchers are working here, and we may implement this project on distributed HPC in future as well. And this is the another project in which we have to identify the historical path of vehicle, means how they are changing the lines, from where the vehicles entered, from where it is going to exit. All this historical path estimation we identify in this project. And second task is basically the land detection, means here we are detecting, here you can see in these pictures, we are detecting the lanes, that in which lane this vehicle is running or moving, right? And third is basically the headway detection, means we have to detect the distance between the vehicles as well, means how much distance among these vehicles, but if they are both are in the same lane. So this is the another approach and another project that we are working on here at Sakra Ivy University at Crab Lab, and maybe this is again we will implement in distributed HPC in future. And third one is basically the AI for COVID. Here we are just identifying the COVID patients, and we are detecting the COVID patients by using the cough sounds basically. This is the third project which is in pipeline that we are working on. And similarly, we have RoboNerds through which you can, this is also AI related project. So and precision agriculture. So these all are the projects that we are, planning to implement on this distributed HPC. But when we are talking about our local infrastructure, is not enough to deal with these huge type of data sets, huge type of where huge processing or computation is required for these algorithms, where we have to train these AI algorithms and achieve the some results. So these all are the projects that we are planning to implement in future for our distributed HPC. So I hope you got some idea about our AI related research here at Crab Lab, and thank you very much. So if you have any question, you can ask. Thank you.
Thank you very much. That was a fascinating presentation. I think we're all looking very much forward to building out the Asia Connect project and being able to provide you with some more compute resources to do some cool stuff with.
Yeah.
Does anyone have any questions for us, If? Maybe I can hit you with one. Are you looking at any other sort of, one of the presenters in the e-culture working group yesterday had a quite innovative chatbot that he was using that he'd programmed with TensorFlow. I was just wondering if you'd encountered any projects like that. He was using it as a teaching aid. To remind students when they needed to be.
One of our student, Andrew, he made the chatbot for our Sakraibi University. So if you have any questions related to the admission, related to the other things, you have queries. So one of our students worked on that, and they have the final year project, you can say thesis. They are working on that chatbot, and maybe soon it will be finalized, and they will implement in our website, so through which you can get the information. If you have any if you want to know about something, you can interact with that chatbot, and you will get the information related to the Sakraibi. So currently that is in progress, and we are working on that as well. Yeah.
Excellent.
Yeah.
Do we have any other questions? Okay, let's move on to our final presenter, Mr. Bernard See from NSCC in Singapore. Bernard will be delivering an update on Singapore and also on the Data Mover Challenge. So over to you without any ado, Bernard. Bernard, are you there?
Hello?
Hi, Bernard, we're ready for you now.
Sorry, I had to attend a biological call. Warm greetings, everyone. I am Bernard from National Supercomputing Center. Let me share my slides. And I'll be sharing the APRP Singapore updates. I'd like to thank Andrew, Francis, and Moon for their help in getting me here today. Can everybody see my slides?
Yep, we're coming through loud and clear.
Great. Okay, before I begin, I'd like to share a little bit about my organization. NSCC is listed as a national research infrastructure under the Research, Innovation and Enterprise Funding of the NRF, the National Research Foundation in Singapore. NSCC is Singapore's first petascale facility since 2015, providing national level HPC resources to national research initiatives from the research institutions, institutes of higher learning, and the industry. So in addition to our founding stakeholders, the Agency for Science, Technology and Research, and 3 of our local universities, a number of research institutions have also signed up as stakeholders. These are the Met Service Singapore, the Technological Centre for Offshore and Marine Singapore, and the Singapore ETH Centre. NSCC also has MOUs with HPC centres in Finland, Japan, and Australia. In addition, we have partnered with research institutes such as the Centre for Quantum Technologies and A*STAR for the research and development of quantum computing and its use in quantum key distribution for secure communication. NSCC is thankful to Singaran for our connectivity to the research and education network by which our users are connected. This is facilitated by the Singaran Open Exchange with the presence of the second point of presence, We have resilient connectivity, high-speed connectivity to our core users. With the aging of our 1 petaflop Aspire 1 supercomputer, NSCC is now in the process of taking delivery of a HPE Cray YAC system, which will be our second petascale HPC system. And this will be followed by the possibility of a third system by 2025. The Special Interest Group for the Science DMZ and the National Research Platform was formed to deliberate the features, architecture, and implementation of a NRP SDMZ infrastructure that will benefit the research and education community in Singapore. This will be through collaboration of the Institutes of Higher Learning and research organizations. The first deployment at NSCC's new data center at the National University of Singapore is still under discussion due to COVID-19 delays. The implementation of the Science DMZ aims to move large amounts of data sets from outside the network through high-performance DTNs with high-speed storage and connected to distributed HPC in NSCC's data centers and data backup at NTU. The large data transfer infrastructure and training project funded by AsiaConnect was completed in December 2021, deploying DTNs in Singapore, Indonesia, Philippines, and Thailand to facilitate research collaborations among domain experts, considering the large data sets transfers between Asia and Europe and the US. AsiaConnect has also organized several training courses and workshops on DTN systems in 2021. Moving data is an essential foundation of national and global science. The International Data Mover Challenge is a competition organized by the National Supercomputing Center Singapore that aims to bring together experts from industry and academia in a bid to test their software and solutions for transferring huge amounts of research data. DMC21 is the third in a series of Data Mover Challenge competitions which started in 2019. It is a biennial competition organized by NSCC. The DMC competition encourages international teams to come up with the most advanced and innovative solutions for data transfer across servers located in Singapore, Australia, Europe, USA, South Korea, Japan, and Saudi Arabia that are connected by 100 gigabits per second in international research and education networks. The challenge focuses on optimizing point-to-point and point-to-multipoint data transfers between sites, a crucial step forward in advancing research collaboration and sharing. The Data Mover Challenge network in 2019 focused on extending VLANs across international networks to create a virtual path between the systems. Moving forward, the extended VLAN methodology will be deprecated in favor of instrumenting and tuning end-to-end production network services to support robust production quality deployments of national, regional, and international exascale data transfers. In 2021, DMC used BGP on layer 3, and the network topology expanded to include CAUS in Saudi Arabia, University of Amsterdam in the Netherlands, ICM in Poland, and multiple 100G links with Australia were added. You can see from this dashboard from the Prometheus that the memory-to-memory transfers during the challenge could reach more than 90 gigabits per second. Gigabytes per second. This MetDash monitoring and debugging dashboard by Persona shows the status of the network within the DMC network topology for loss, trace routes, and throughput. In terms of scoring and how the participants are judged, we are focused on 3 areas: error-free data transfer performance using MD5 checksum for data integrity verification, memory-to-memory transfers, as well as disk-to-disk transfers in both directions. The second area is on technological innovation of the solution in areas such as disk management, access management, protocol adaptability, OS scheduling, among others. And lastly, the area of end-user experience, including the user interface, ease of installation and use, licensing model, and integration with services such as Access Federation. For DMC21, participants were assessed and awardees were selected by an international panel of judges comprising domain experts and professionals in the field of networking and data transfer. The members of the judging panel are Andrew Howard from NCI Australia as the chief judge, Professor Kees de Laat from University of Amsterdam in the Netherlands, Associate Professor Francis Lee from NTU Singapore, Emeritus Professor Lawrence Wong from NUS Singapore, and Tin Chang from JISC in the United Kingdom. Supercomputing Asia is an annual conference that encompasses an umbrella of notable supercomputing and allied events to strengthen local, regional, and global cooperation in HPC technology. SCA 2022 was held at the Suntec Convention and Exhibition Center last week from the 1st to 3rd of March, where the awards for the Data Mover Challenge 2021 were presented to the winners. The winners for the recent challenge covered the spectrum of network technology, and the quality of the entries for DMC21 were highly regarded by the judging panel, with each presenting its own merits in various use cases. The overall winner with the best long-distance performance was awarded to the team from Siena, the International Center for Advanced Internet Research, ICAR, and Utah Education and Telehealth Network. The team who produced the highest consistent throughput, especially over long distance from Europe to Australia. Team Musashino from Japan, comprising members from the National Institute of Information and Communications Technology, Killer Technology, and Kyoto University, Japan, created a new internet protocol which was able to deliver a reliable data transfer service over a range of network conditions like loss and congestion. For their entry, the team won the Most Innovative and Best IPv6 Performance Award. Team Architecta from Australia optimized their solution for large reliable dataset replication within an existing data management framework. With good system architecture design, Team Architecta won the Most Complete Solution and Best Software Architecture Award. For good end-user software design and architecture, the award for Best Integrated Software Experience was won by Team Globus from Argonne National Labs and the University of Chicago, USA. For their good exploitation of containerization, the award for Best Virtualization Support was won by Team Fastest Group from Robust HPC, Malaysia, and Shenzhen Ray Vision Technology. Before I conclude, I would like to thank all our supporting partners at DMC21 for their cooperation and hard work in coordinating and setting up the infrastructure for this event. I thank you for your kind attention and hope that you found the presentation informative, and have a great weekend.
Thanks, Bernard. A great presentation. And I'd like to thank you for the massive amount of hard work that you put into coordinating the technical teams behind the scenes, collecting all the data and wrangling all of us judges to be there on time and to supply us all the information. Thank you very much. So we're running a little over time, so I'll hand back over to Jong-hoon for some concluding remarks. Thank you, everyone. Goodbye.